Welcome back to our Tech Bite series. Today we have Nick, who'll be telling us a little bit more about spectroscopy. So Nick, let me start by asking, what exactly is spectroscopy?
Hi Victoria, and good question. Spectroscopy covers a wide range of techniques that are used to analyse and understand the structure and properties of matter. But to put it simply, it's the measurement and investigation of light and how it interacts with matter. Generally, there are two types. Firstly, there's absorption spectroscopy, which measures how much light a sample absorbs, and it's used to determine the presence and sometimes the specific amount of a particular substance in a sample. The other is emission spectroscopy, which measures the emitted light from your sample once it's reacted to or been excited by your input light. And because the emission spectrum is different for each chemical element, it can be used to determine the composition of a material.
So can you use any form of light to do spectroscopy?
Essentially, yes, but to understand how any portion of the electromagnetic spectrum interacts with matter, be that high energy gamma or X-rays, or through the UV, visible, infrared and beyond, ideally we want to be able to use just a specific wavelength or narrow band of wavelengths. Since the time of Sir Isaac Newton first observing how white light is refracted upon passing through a prism, we now have many different components available to split light, and also to utilise individual wavelengths, including filters, diffraction gratings or monochromators. And today we now have a multitude of sources of EM radiation available, such as LEDs, halogen and xenon lamps, lasers, X-ray and infrared sources. But there's also plenty of naturally occurring sources of EM radiation too, including fire, light from the sun, distant stars and galaxies, radioactive materials, and even bioluminescent organisms. So yes, the light you use can essentially be anything, but usually most spectroscopy applications would utilise UV, visible or infrared light.
You mentioned different components are required to perform spectroscopy. So what sort of instrument would these typically be in?
So generally you'd use an instrument called a spectrophotometer. This would include the light source, internal optics to split and focus the light, a sample chamber, a detector, and readout electronics to process all the information. Light could be absorbed or emitted, or even reflected or scattered by the sample. So the type of spectroscopy you perform and the overall system you use will vary depending on this. You also need to consider that your sample will react differently to different wavelengths and intensities of light. And the light signals you observe could be quite strong or they could be very weak. So using the right light source and detector is very important. And finally, it's very common for a spectrophotometer to contain a combination of light sources and detectors so that the one system can perform analysis across a wide spectral range.
Okay, great. So I guess we'll come into the all-important question. What sort of light source and detector would you need for spectroscopy?
Where to begin? Firstly, because spectroscopy is so sensitive, it's important that your light source and detector are good quality in order to get the most out of your measurements. This means having a highly stable and often high intensity light source paired with usually a high sensitivity and low noise detector. And Hamamatsu offers hundreds, if not thousands, of high-end light sources and detectors to suit the most demanding requirements. So light sources, these can either be line or broadband sources. Line sources emit light at a specific wavelength, and these would include hollow cathode lamps, LEDs for lower intensity, or lasers for higher intensity applications. Broadband sources are probably more commonly used and emit light across a wide wavelength range, which can then be fine-tuned to utilise just a specific wavelength or a small band of wavelengths. That means you can use just that one light source for many applications where you need to make use of different wavelengths to interact with your samples, so that would help to reduce overall system costs. Typical broadband sources include deuterium lamps, which are high-intensity UV lamps, xenon lamps, which are long lifetime lamps with varying intensities for UV, Vis and NIR, or supercontinuum sources, which are high-intensity laser-based sources, again for UV, Vis and NIR. And Hamamatsu's new NIR supercontinuum source offers industry-leading stability to help give you the most accurate measurements. But Hamamatsu also offers a fantastic range of innovative broadband light sources called the laser-driven light source. This uses the unique method of utilising a laser diode to ignite and maintain the plasma inside a xenon lamp, which then outputs light of extremely high brightness and stability from a very small spot size over a wide range of 170 nanometers up to 2.5 microns. More will be said about this in a future Tech Bite, so be sure to check that out. But in the meantime, do check out our website for more information.
And what about the detector?
So for most spectroscopy applications, you have the standard option of a silicon detector, which offers high sensitivity from UV to NIR in the range typically from 190 to 1100 nanometers. These come in the form of photodiodes, a CCD or CMOS image sensor to capture the whole output spectrum, or then even a complete mini spectrometer, which also includes internal optics and signal processing, making your setup much easier. If focusing just on the infrared, then we also have many options here, including InGaAs, photodiodes, image sensors and spectrometers, which cover from 900 nanometers up to 2.6 microns. But then onto newer compound semiconductor detectors, such as our InAsp detectors, which offer high sensitivity as far up as 14 microns. These have been developed specifically to replace older technologies based on lead and mercury, which will soon no longer conform to the new RoHS directives for hazardous substances. So that makes them especially appealing for new developments in MIR spectroscopy, as the demand continues for greener and more environmentally friendly products. But for the most demanding of applications, where you require the highest level of sensitivity and lowest possible noise, you can't really look any further than a photomultiplier tube, or PMT. PMTs work from UV to NIR up to 1700 nanometers and come in all shapes and sizes. But what makes them special is they have an inherent gain mechanism which multiplies your incoming light signal by a factor of over 1 million without affecting the noise levels, so that makes them ideal for any low light level application, not just spectroscopy. Hamamatsu is the global leader for PMTs, and they're the ultimate in sensitivity, and they will be for many years to come whilst other, newer technologies still try to play catch up.
Impressive explanation, Nick. So to finish, can you explain what makes spectroscopy so special and vital in today's world?
Absolutely, and as you've heard, spectroscopy investigates how light and matter interact. This happens everywhere, all the time, but pure spectroscopic analysis helps you to understand the fundamental composition and structure of matter, be that on atomic, molecular, or even astronomical scales. This makes it both extremely sensitive and extremely useful. For example, you could use spectroscopy to analyse the atomic structure of something, to perform gas analysis for industrial, health, or ecological applications, to study the structure of drugs in order to improve their effectiveness, or to measure compounds in solutions, for example, drug and trace explosive detection in airport security. You could use it to perform water or materials analysis, to characterise proteins and DNA structure for forensics chemistry, food and beverage inspection, archaeological and agricultural analysis, atmospheric and earth science, or even to measure spectral emission from distant stars and galaxies. This is just a small list of applications, so I think you can begin to understand why spectroscopy is so incredibly useful. And it's something most people would have seen or experienced, just like in those tests performed every day at airport security. As we're a global leader, it's highly likely you've come across a Hamamatsu product without even realising it. And as Richard mentioned in his Tech Bite on how Hamamatsu is helping in the fight against COVID-19, we may not be a household name with the general public, but we're a company that influences so many aspects of our daily lives. Hamamatsu is continually pushing the boundaries of photonics technology through both our R&D and the releasing of innovative products and technologies for existing and new applications, and will continue to do so for the benefit of all of us.